the polarization of reflected light varies up to object material and geometry. For this reason, polarization photography plays a crucial role in the fields of shape from polarization, reflection removal, and so on. Nowadays, we can capture a polarized color image within a single shot with the on-chip polarization sensor. The light transport through the alpha polarizer is formulated as a cosine function. Thus, the sensor's bilayer layout causes lower photon counts and signal-to-noise ratio. And the polarization information is sensitive to noises. While we try to use a learning-based approach to handle the noise, it normally requires labor-intensive data collection. In this work, we construct a physics-based noise model for polarization sensors to generate synthetic noise data from clean images. Extensive experiments demonstrate that the model trained on synthetic data can restore more detailed signals and polarization information compared to real paired data. Then, we introduce our method. We apply a physics-based noise model, which models the noises introduced in the imaging process from the photon to the digital signal. In total, the noises include content-dependent shot noise, and content-independent readout noise, row noise, and quantization noise. The noise components are modeled using Poisson distribution, Tukey lambda distribution, Gaussian distribution, and uniform distribution, individually. As polarization color images contain information that can be separated into 16 channels. It's an intuitive way to analyze the noise model of each channel. By calibrating the parameters of the model of each channel, some specific properties are observed. We first observed variances between the channels. As shown in the box plot figures, we show some examples of sigma b, mu, and sigma tau. The analysis shows the need to model the channels individually. Then, by computing Pearson correlation coefficients of parameter samples, the heat maps show that the mu and sigma b of red and first green channel, blue, and the second green channel are highly positively correlated, while the other combinations are nearly uncorrelated. From the observation, multivariate Gauss distribution is applied to fully formulate the parameter sampling. The model of mu and sigma b are thus formulated with a multivariant Gaussian distribution, and sigma tau is modeled as 16-dimension Gaussian function. Moreover, we noticed that the parameters linearly change by gains. Especially a global bias decreases rapidly below the black level with lifted gains, k. We use the least square method to fit the linear system. After fully formulating the noise model, we generate noise data from clean images for model training. To enable the research on polarized color image denoising, we collect a dataset under outdoor low-light environments. 824 low-light images and their corresponding references are captured in total. Given a low-light noisy raw polarization color image, we first subtract the black level and global bias from the input. We will show that subtracting such a global bias benefits polarization image denoising and polarization information restoration. And then we enhance its intensity by a relative ratio. At the last, we apply a denoiser model to restore clean data. For better polarization color image restoration performance, a transformer-based neural network is proposed, which combines attention modules in both spatial and channel domains. Shifted windows and shuffled heads are used for cross-window and channel communications. We train models on real paired data and synthetic data, and conduct evaluations on our test set. As shown in the table and figure. The star symbol stands for the model trained on our synthetic data. Regarding the visual comparison and quantitative comparison, the traditional method is to restore signal and polarization effectively. A model trained on our synthetic data can restore more detailed information compared to that trained on pair real noise data. And our network performs better on both restoring clean images and precise polarization information in most scenarios. We further conduct ablation studies. The comparison of paired data with and without global bias shows that by subtracting the global bias, more vivid image and polarization details can be restored. By comparing data generated by different noise integrations, as shown in the table, A full noise components deliver significant and stable performance improvements. The star symbol stands for synthetic data using channel-wise biases. At the last, we demonstrate the effectiveness of our denoising approach by feeding a noisy and denoised polarization image into a 3D shape reconstruction network. As illustrated in figure, compared with the noisy input. The 3D normal reconstructed with our denoising process contains a more detailed structure and accurate shape. In this work, we address the low signal-to-noise ratio issue in polarized color sensors. We capture a real-world dataset of paired noisy and reference images. Analyze noise sources and generate realistic noisy images for training. And our denoising process benefits polarization applications. Thanks for your listening. Please refer to our paper for more details.